Oliver Schauerte majored in mechanical engineering and received his master's degree in material sciences from the Ruhr University Bochum and his PhD from Technical University Hamburg-Harburg on the fatigue behavior of a high-temperature titanium alloy. Dr. Schauerte, the stage is yours.
Thank you, Mr. Kreh, for this kind introduction. Ladies and gentlemen, it's a great honor for me to have the chance today to talk to you about our research activities at Volkswagen in material sciences, but especially sure about the applications of powder metallurgy today and hopefully also very much in future. As I think many of you are aware, in many fields, automotive industry has been a driving force, a driver for materials innovations in many aspects. Don't think only about materials innovations in case of new steels in the body in white or for new aluminum alloys for engine blocks, but there's also many little things you are not aware of that have been very much driven also through automotive industry, like transparent coatings on functional layers, like the alternative drivetrains, where we need a lot of material innovations for both for fuel cells drivetrains, but also for electrical drivetrains. It's the functional materials, and sure, it's the lightweight design, it's the lightweight technologies that we have for new high-strength steels, for advanced aluminum alloys, and other materials. Just an example that has nothing to do with powder metallurgy, but for example, we are more and more introducing hot forming technologies and hot form steels with high strengths up to more than 2000 MPa. And these steels that we are using as the outer shell of the car for the body in white are also coated. They are coated with a paint. They are coated with a paint, with a primer, filler, base coat, and so on. And the complete coating has just the thickness of a human hair. So the technology development in these times have been very progressive. Now, also give me the chance to do a little bit showing off. I'm working for the Volkswagen Group. Volkswagen Group is one of the largest car manufacturers in the world. We are producing in 109. We have about 600,000 employees, and we have 119 production sites worldwide. Most of them producing cars. Many of them also just producing automotive components. The number you should keep a little bit in mind is that we are manufacturing more than 38,000 cars per working day, and each one containing powder metallurgical components. For those who are not that familiar with automotive industry, Volkswagen Group is not only consisting of the brand Volkswagen itself, it contains also the high-volume car manufacturers Audi, Skoda from Czech Republic, and Seat from Spain, and then also the sports car manufacturers Porsche, Bentley, Lamborghini, and Bugatti, the Italian motorcycle brand Ducati. And on the commercial business, we have the small commercial cars at Volkswagen Commercials, Volkswagen Nutzfahrzeuge, and the heavy trucks and buses at Scania from Sweden and from MAN. But I think many of you will not know, but MAN is not only a manufacturer of buses and trucks, but it's also the largest manufacturer of stationary power units and especially of ship engines. Now, I myself, I'm responsible for materials research and manufacturing processes at Volkswagen Group Research. Volkswagen Group Research is based in Wolfsburg and has about 600 researchers based there, and is financed by and working for all the 12 brands of the Volkswagen Group. We have also some affiliates. Most important, I think, it's the Volkswagen Electronic Research Lab that we have in Palo Alto, right in the center, right in the heart of the Silicon Valley for new electronic trends. And we have also additional offices for new materials, especially for new drive concepts here in Canada, and then a general investigation office in Shanghai in China, and a small office at Tokyo. Now let's talk about material sciences, what we are working on. And this was a little bit surprise for us that we realized when we were preparing this presentation for the World Powder Metallurgical Conference that we work relatively little on powder metallurgy, nearly nothing, because all the components you are working for and the components you are making, they are normally supplied to a supplier who supplies it to another supplier and who finally supplies to us the complete the complete assembly for putting it into the car. So we thought that we have to deal definitely more with powder metallurgy. However, where we are working actually, I think as a metallurgist, steel in general is one of the most exciting materials still, and still one of the most promising materials. And I would predict that even in 20 years, 95% of the cars will be mainly made of steel. So we have to definitely deal with new steel developments. We also work on light metals, more on magnesium actually, on magnesium sheet material, less on aluminum, but this is because Audis also have still a center of excellence for aluminum making, aluminum components, and we work also a little bit on titanium. On the polymers, we work with plastics, mainly for low volume investments, for low volume, for low cost investments, for high volume production, to simplify just the assemblies, to bring together several parts in one single assembly in one manufacturing step. And we are also working on fiber reinforced plastics, and sure also on joining technology and on functional materials. Now, how do we work? In the past, it was more a kind of a knowledge-based development or an experience-based material development. Today we are coming more and more to a data-based material development. We must become faster in material development processes for automotive production. It is not acceptable that we need 10 to 15 years to develop a new material and then another 10 years to bring this material into our cars. To speed up in this development, we are working more and more with simulation methods, not only on complete components, but only on the manufacturing processes like a draping simulation for fiber reinforced plastics or in casting simulations. We try to predict the material's behavior and microstructure simulations directly in the development of the material. And sure, we are also working on, or today we are also working since a few years on quantum simulations, so we go in the subatomistic level. Now, why, a little bit surprising maybe, is an automaker working with quantum mechanics? The simple explanation is that the quantum mechanics describe all the material properties. If you have understood how atoms and nuclei interact with each other and with the atoms in their neighborhood, you can predict the material's behavior in absolutely every aspect. But this needs a lot of computer power, and the programs are relatively new. However, we try to increase the speed in material development, more on functional material, but beginning also regarding structural materials, to predict these material behaviors and to speed up material development processes. Now, let's talk a little bit more about powder metallurgy. That's the reason why I'm here. I don't think that this is the right place that I tell you what powder metallurgy is used for. However, a short view, where do we find the most of the powder metallurgical applications? It's in the drivetrain for connecting, for valve control, in the fuel actuators. You find actuators, you have part in the gearbox, and you find, sure, also parts in the brake system, and for example, in the seat adjustment. What kinds of technologies are used for this? Also, this is quite well known for you. First of all, and I think for most of these applications, we have to talk about, we have to talk about the classical powder metallurgy, so compressing and sintering technology, as used for engine parts, brake system, and so on, and in future probably also for fuel cell components or for electrical engines. More and more important became in the last 20 years metal injection molding processes for geometrically complex components, such as a turbolader charger here. Often not considered is the use of powder metallurgy for coatings, so for wear resistance, to improve wear resistance, or to apply protective coatings for thermal protection. And now, as mentioned also by the other speakers, it's the additive manufacturing technology to integrate functions and to have the chance to make a component without any tooling costs, directly made to the fitting shape, to the necessary shape. Again, back to the typical powder metallurgical components, we see that if you look the world market on powder metallurgical classic components, that more than 70% are made for automotive applications, and that we find more applications even for industrial engines and for work tools for tools. We like it because it has a very competitive price and because it has a very good material yield, and finally you make the parts with a very good and constant quality right to the necessary shape, final shape. Another big field is the metal injection molding. As here, I have here some samples that you can use, like adjustment rings for turbochargers, like locking systems as it is used in the roof mechanism of a convertible. Millions of them, hundred thousands of them are made, and even millions, many millions are made just for the roll levers in the valvetronic system, so in the valvetrain control, or even here in the seat adjustment. We get a very high surface quality, and we have a high diversity of materials, and we can make a very complicated geometry bring directly to the part size with a high dimensional accuracy. Now, these are the classical technologies that are used in our cars and that will always be used in our cars, but as a materials research, looking for what will be happening in the future, we should also look for the new processes. As a material research, we are mainly interested, by the way, for those technologies and materials which we expect that could come to production in a time frame between 5 and 10 years approximately. Now, some of the speakers already mentioned the additive manufacturing, the metal additive manufacturing, still interesting, but don't think always just about metal printing, 3D printing, by buying a 3D printer and make a component directly. Why not thinking about components that you can't completely manufacture in a forging technology or in a casting process, but you can make the base component and bring it to a 3D printer and then just apply the components or the part of the component that you can't manufacture with a classical manufacturing process. This is what we would call hybrid manufacturing, so you combine different manufacturing process. When five-dimensional machining of bulk material was invented, nobody got the idea to make the complete car from a machine shop. That's the same on 3D printing. You don't have to make the complete car from 3D printing, but you have to use 3D printing where it is really useful. Useful it's also in the case of repair and spare parts. If a repair part runs out of stock, it's interesting to make them, instead of investing in new tools, or to repair the old tools, to make the parts directly from 3D printing. This is both for polymer 3D printing or for metal 3D printing. Super sports cars, but also low volume cars, as you find them sometimes in truck or bus business, could be made easily or individualized parts by 3D printing. And finally, it's also a chance to functionalize material, could even print sensors, or you can print materials that contain the sensor already inside, or you can make even new materials by 3D printing. So it's there's a very promising future for this technology. How do we deal with the problem? We have one big problem in 3D printing today, in metal 3D printing, and now just a look at the actual scientific work we are doing at Volkswagen. This is the typical powder we are facing when we have to make powder components. So you see here it's about 10 microns. The particles about 10 microns thickness. They have to be spherical. They have to have a very homogeneous shape, a size distribution between 20 and 63 micron. And so you have already in the atomizing processes a number of significant material loss. This whole thing, if you just compare to classical sintering processes or press process, as you have in the green part, where you just accept also spherical part, where you accept parts with a complicated shape, which are flaky, which have dendrites, and you even are happy if they have an irregular shape so that they very good stick together in the compressing process. The high demands for the powder we use for 3 metal are resulting that we have a smooth surface in the 3D printer, that we have a continuous production process in each layer, that we have exactly the same shape in the molten region. But this results in prices between 80 and 120 euros per kilogram powder for a standard tool steel like a 12709. So this is a price level that we can't deal with today. So we have to think how we can reduce the costs for powder metallurgy for automotive applications. Our approach here is in a first step, that we simply accept, instead of the very, very homogeneous powder, that we also accept powder particles with an irregular shape, that we accept also powders that are smaller than smaller powder particles, which are smaller than 20 micron, and then by adjusting the parameters in the 3D printer, we have been able to create also from this powder good material specimens with a yield strength which is approximately on the same level than we find it with a standard powder. And for the next steps, we think about using the property optimized powders. For example, we have even a higher grain distribution, we have better printers, and we have a pre-alloyed powders, or we even modify the powders and use more heterogeneous powders. Please also think about having in a printer in different positions, different powder blends or different powder distributions, so that you can change or influence the properties of within one single components by changing just the alloying elements in the powder. Now coming to the second important driver for automotive industry. Today, automotive industry, we are facing we are in a tremendous change in automotive industry. It's driven by the autonomous driving, it's driven by new mobility concepts like Uber, like car sharing and so on. And finally, it's very much driven, and this is important for us, by new drivetrains. If we look, for example, what we have to expect already in 2020, the limitations, the challenges and the limitations by law in the different countries will be very, very hard, and they will be much harder in 2025. And to be honest, to reach these limits for a family limousine is with a classical internal combustion engine nearly impossible. So we are forced by law to apply additional alternative drivetrains, either electrical drivetrains or fuel cell drivetrains. And if you have seen the news on the weekend, there are a number of politicians who intend or who would like to give a ban on internal combustion engine cars from 2030 totally. I don't know what they thought about, but they definitely didn't think very much about jobs. However, this will mean that it's a kind of an average prediction of different scenarios, that this line will even shift up to here. So in the middle of 2020s or in the 2030s, we will face a situation that 30 to 50% of the cars will either have a range extended electrical vehicle, or will be a battery electric vehicle, or will be a fuel cell electrical vehicle. And this will change dramatically also the situation for the supplier industry, not only for us. And the question is, will it be possible to have all these electrical vehicles available for the customers? And yes, battery technology itself is doing very good progress. So we think that we will be in the middle of until 2020, we will have 650 kilowatt per liter battery power. So we will have a range for a standard vehicle of nearly 500 kilometers. And new concepts like solid-state batteries will probably also allow to go to 700 kilometer range in the middle of the 2020s. So the progress the battery development is doing, although you don't realize it directly on the market or in the available what you can directly buy, but the progress is very, 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 very fast. Please think, when we think about a car cycle, we think about a development time of 4 to 5 years, and then we would like to use such a car technology 8 or even 10 years. And if you then talk about 2025, it's tomorrow. It's today, it's the date. Today is the day where we have to talk about these technologies and to make the decisions, also the strategic decisions. Now coming back to powder metallurgy. What does all this mean to powder metallurgy? You have seen how many cars we make a day, and you have seen that 70% of the powder metallurgical parts you are manufacturing or we are manufacturing are used in automotive industry, and most of them in classical internal combustion engine or gearbox. This business will definitely shrink. So we have to see that we find new applications, that we find new ideas for powder metallurgy in automotive industry. Typical applications could be the fuel cell system, there could be the hydrogen storage, not the tank itself, but a lot of valve units will be highly stressed in use and could be made in powder metallurgy. We have to see about the battery system itself, I will later talk about, ensure the electrical engines themselves contain powder metallurgical parts. Just as an example, this is a typical electrical drivetrain, and if you have the rotor here, already today made in powder metallurgy from neodymium iron boron magnets. Neodymium iron boron magnets are still the most powerful magnets that are used, or let's better say, instead of neodymium, rare earth. The problem is that the prices for neodymium are changing very much. Rare earth, only a few countries in the world have the rare earth market under control. So for the automotive industry and for our suppliers, it could be, from a strategic point of view, it can be very interesting to have different heavy rare earth materials like dysprosium or terbium available that could replace neodymium in our hard magnet systems. And then also soft magnets, it was already mentioned. It's today, most of the soft magnets are simply soft magnetic sheet that is used, for example, for the rotors in electrical engines. But in the future, we will also think about having composites, soft magnetic composites, so powder metallurgical soft magnetic anisotropic material is compressed with a polymeric binder in an appropriate shape so that it can fit it precisely into the electrical engine and could do its work there. And then finally, also a view in the future, a little bit more complicated. If you think about lithium-ion batteries, for the cathode we need a blend, a powder metallurgical blend consisting of nickel, manganese, and cobalt, or on nickel, aluminum, and cobalt. And these powders have to be mixed in a certain way, because the problem is that nickel is, from the electrical point of view, from the charging point of view, nickel is the best material. It has the highest loading capacity, but it also has the highest risk to burn. So in case of accident, if such a lithium-ion battery burns, you can't stop it burning. It will produce its own oxygen. It simply doesn't stop. To avoid this, which is for the safety reason, has for Volkswagen, I think for most others also, has the highest importance, you reduce the electrical capacity of these materials by applying manganese and cobalt. So to overcome this problem, one approach for the future are completely new powders. You see here with the powder particle is a so-called core shell material. So on the outer side of these cores, you have a nickel-rich layer to have the electrical activity, but to provide safety, you want to reduce the volume. You want to reduce the share of nickel, and this you achieve by having a core that contains more manganese and cobalt. This is a high-tech powder developed for the future, and I think maybe also a nice idea how powder metallurgy can become more scientific and can be productive and contribute to the e-mobility of the future. And so that's already nearly the end of my presentation. I'm happy to sum up a little bit. So until today, the majority of the powder metallurgical manufactured parts are produced for the automotive sector, and this will also be done in future. Powder metallurgical parts remain one of the important drivers for highly stressed components, for wear stressed performance, but we have to face the fact that the classical combustion engine and gearbox will sooner or later, hopefully a little bit later, come to its end, and so we have to think about alternatives for powder metallurgy in automotive production, such as selective laser melting, so the 3D printing, or the new electrical drivetrains with a number of applications. And finally, I would like to thank you to come together here in Hamburg and to discuss all these options, and also to invite you to talk to us, to the automotive industry, to Volkswagen, so that we together find solutions and that we together find new perspectives for powder metallurgy and for your business also within the automotive industry. Thank you very much.